Hello, welcome to Introduction to Medicine. This is the Biostatistics module that will be taking place this week. It's going to be one heck of a marathon. We're going to march right on through the entire textbook this week. We'll be covering 3 chapters today and more or less probably 2 chapters a day all the way through Sunday. When you look here, this is just an estimate of where we'll be. Some of these topics may take a little bit less time, some a little more time. Uh, Generally, you're going to need to read every page in that book, do the problems that are in there, and just work your butt off to get through this stuff. My name is Malcolm L. McCallum. I'm a PhD. I do a little bit of research in biostatistics, physiology, and other areas. The textbook we'll be using in this class is listed before. If you don't have it yet, you better get it ASAP because you're going to need it. Biostatistics is pretty darn important. It'll make you a better doctor if you know biostatistics, and in general, most people would probably be better citizens if they had a better grasp of statistics in general. So we'll start talking about this topic now. I'm pretty sure that some of you sitting out there who are going to be doctors someday are sitting there saying, why am I taking biostatistics? I'm going to be a doctor. I need to know physiology. I need to know how the body works. I don't need to know a bunch of statistics for crying out loud. Well, I'm sorry to rain in your parade, but you're wrong. In fact, there was a research study done just a few years ago, and I have the citation down here if you'd like to go look it up. It's easy to find using Google Scholar. It was published in Statistics in Medicine in 2009, and they surveyed 130 physicians. Well, they actually surveyed more, but 130 responded. And of those 130 physicians, 90% found that statistics were useful in their job. 79% considered it important to their work, and 63% said that there were things that they did that could be done better if they improved their knowledge and understanding of statistics. I think this is a pretty telling study that if you want to be a doctor, it's very important that you understand statistics, because if you can understand statistics, there's a lot of things you can do that you can't do if you don't understand statistics. The doctors in that study were surveyed, and they were asked what kinds of things could they do better if they had statistics. And of course, one of the real important things doctors said was that they would be better able to critically evaluate other people's research. Doctors don't just sit around and treat people like on Gunsmoke or something. Doctors need to be continually reading over the literature so that they understand exactly what it is that the research says right now, so that they can apply that to treatments on a daily basis. So it's important for them to be able to evaluate what research is published. Also, some of the doctors said that it would allow them to actually become involved in research, because by understanding statistics, they could actually design a study or participate in a study in a more active manner. And this is probably not of interest to all physicians, but some of you may come through and decide, hey, I kind of would like to be involved in some research. There's other things that doctors said. Some said having a better understanding of risk. And of course, risk is a very important thing. When we start talking about giving someone medicine, there's risk to giving them medicine and risk to not giving them medicine. There's a risk to allowing someone to walk around out there with a disease or to quarantine them. So there's all kinds of risks involved in medicine and the treatment of people who are sick or healthy. Injuries. Should we treat this injury? Someone may say, well, what happens if I don't have it fixed? Well, it's just important to understand what the risk is of treating something as the risk of not treating it. So these are very critical things for the doctor to know, and they use statistics to do this. Further, doctors said that they may be actually better able to explain things to people. If you look over here on the right at this comic that I've posted up here, and you read that, you see that it's pretty darn difficult to understand what that person's saying if you're just a a guy off the street. Maybe some of us who have a good, strong math background get it right away, but the rest, probably not. When we start talking about statistics and the idea that it's just common sense, it's important to understand one very basic concept from logic, and that's called Sorokin's razor. Sorokin's razor is the idea that when you're faced with two possible solutions for a problem, the most obvious one's probably true. For example, if I walk into the kitchen, there's a little kid there, and a broken cookie jar and cookies all over the floor. Uh, I heard a big crash just before I came in. Odds are, who broke the cookie jar? Could it be someone else? Could it be the dog? Could it have been aliens? Sure. But the most likely answer, the one that's most obvious, is that the little kid is sitting next to the cookie jar, cookies strewn all around his feet. He's probably the one that did it. Another example, if we look here at this scene from Ghostbusters, we know if I see a big stack of books sitting in the middle of the library like this, how'd the books get like that? Most likely idea is someone was pulling a prank and stacked a bunch of books. Of course, it could have been a ghost. Okay? Which book was put in the stack first? Which was placed last? Could a ghost have levitated the top half of the stack and started stacking books underneath just because it wanted to? Sure. But what's most obvious? The most obvious is that when someone's stacking books, the books on the bottom go down first, the ones on the top go down last. This is an obvious use of Sorokin's razor, and we actually use it all the time unknowingly. Regardless, when we make an observation, how do you know what the right answer is? You really don't. But when you use logic and you use common sense, you're going to get probably the right answer in the end, or at least a sensible answer if nothing else. Statistics is nothing more than mathematical expression of logic and common sense. And if you can keep that in mind, it'll make it a lot easier to understand as you go through this. So when we talk about science and statistics and biology in particular, but when we look at science, this slide here really hits home about something very critical. If you don't make mistakes, you're doing it wrong. If you don't correct those mistakes, you're doing it really wrong. If you can't accept that you're making mistakes, then you're not doing science at all. And that's really critical about statistics because in biology, when we start talking about biostatistics, in biology, there's all kinds of variation, and you don't always get the right answer the first time you try something. So repetition is very important, and that variability is very critical to admit that it exists. Just like there's variability in how you can stack books or how people in general stack books, we've said there is variability in biological data. And you can see this when you look at these little graphs here. They don't like just follow a straight line. They're bouncing all over the place. And there's trends, but definitely we don't have the same answer every time we see one of these points plotted. Things in biology don't always work the same way. If you can keep that in mind, you're going to be a lot happier at the end of the day. So now that we understand there is variability, we're going to talk about how we classify data so that we're able to use the appropriate statistics as we go through this class. Data can be divided into two broad kinds. One is called categorical, also known as qualitative data. The other is numerical, and that's also known as quantitative data. Categorical data can also be divided up into two broad groups, nominal and ordinal data, and numerical data can be divided into counts versus continuous data. So first, looking at categorical data is qualitative. We have different categories. Those categories may really not have a whole lot in common. For example, heads versus tails, good versus bad. It doesn't mean that there's a continuum between them. Often they're either or categories. These categories are always going to be mutually exclusive. You can't fit somewhere in between. You're one or the other. Okay? Some examples of categorical data include names. Each of us has a different name. Diseases, cities, hospitals. These are all different kinds of categories, and they all are types of categorical data. Again, categorical data can be broken into two broad categories. The first of these is nominal. Nominal data are categories that they have no particular order involved. They just are a category. For example, hospitals. When we list a series of hospitals, there isn't any particular order that they may come in. We might put them in alphabetical order for convenience, but they could just as easily be in reverse alphabetical order or in some type of random groupings. Patients, diseases, these are all categories and they don't really have any kind of dynamic between one disease to the other. They're names. Houses, hospitals, patients, diseases, they're all unordered. They don't go in any particular order. So besides categorical data being classified as nominal data, categorical data also can be categorized as ordinal data. Ordinal data is a situation where the categories do have some kind of order. For example, people go from first grade to second grade to third grade and on. You don't generally jump from first to fifth grade. I guess some people do, but most don't because of you have to learn the stuff in between. You don't jump from algebra to calculus 3. You have to take calculus 1 and calculus 2 in between. So categorical data can be divided into nominal and ordinal data. Nominal data is just names that have no particular order, whereas ordinal data are categories that actually come in some kind of order. In addition to categorical data, we also have numerical data. And numerical data can be divided up into two broad categories again. Counts versus continuous. Counts are very obvious, and those are integer values. Usually it's like 1, 2, 3, maybe you have 5 apples. That's a count. Continuous data, on the other hand, is a continuum. For example, we can have here the devolution of state school standards. They started really well and they slowly degraded into rodent level. Examples of counts include numbers of sick days or numbers of pregnancies, number of people who are sick. Whereas examples of continuous data would include stuff like how tall you are. One person may be 5'5.2346721, while the other person may be a little bit taller or a little bit shorter. It's on a continuum of some kind. We can also classify data according to how it's scaled. And this is very important because depending on how data is scaled depends on how you might use it or evaluate it. Data can be scaled in two broad different ways. It can be scaled in intervals, or it can be scaled according to ratios. Interval data is a kind of data in which 0 is really nothing more than a placeholder. It doesn't really mean there's nothing there, it's just saying that that spot is the 0 mark. Some kinds of interval data include temperature, weight, tidal volume of breathing. These things are they're a number and they occur in some point along a number line. Ratio data is different, and in ratio data, 0 really is a real number. Ratio involves fractions, calories per gram, cases per 100 people. Ratios involving time are called rates, like miles per hour. When we talk about ratio data, these are numbers that when you have 0, it means there's nothing there. But in intervals, it's just a placeholder along a number line.